Hello, and welcome to the Critical Design Review of Group 8, CHROMA, an assistive lighting system for entry-level photographers. Our team consists of myself, Matt Cope, Juanita Solania Romero, Juan Trochinsky, and Nicole Patel. The spark for this project came from an acquaintance and professional photographer, Lee, who mentioned how difficult it is to accurately photograph performers with dark skin under stage lighting. Once the sun goes down or people are inside and away from natural light, cameras have a hard time capturing dark skin tones without them being washed out. Our solution to this problem is to create an assistive lighting system to throw the correct color light onto subjects with darker skin tones to ensure accuracy when they're photographed. CHROMA's system has three main goals. The system accurately detects the skin tone of the subject, then determines what color changes need to happen to ensure true-to-life capture of the subject's skin tone. The system self-adjusts, reacting to live changes without overpowering the existing lighting design of the space. To achieve these goals, our project has four main objectives. First, we must detect the person. To do this, we create an image capture unit comprised of a multi-lens imaging system to create a portrait-style image, capturing a person from the shoulders up. To light this person, we create an array of LEDs that can change the color, temperature, and brightness of the light thrown onto the subject. For these two systems to work together, we devise a mapping table in the single-board computer for image analysis of skin tone. The input of the table will be the difference between the average RGB values of a subject's skin in the photography setting versus in a test setting of neutral light. The output data is then communicated to the microcontroller unit in the LED driver of the panel. The MCU will communicate through Wi-Fi connectivity and an MQTT program on the ICU's single-board computer. Of course, we want CHROMA to look good, so we have a minor objective of designing a housing to make the product look cleaner.
For this project, we needed a microcontroller unit, also known commonly as an MCU. The main requirements for our MCU were that it be affordable for us to purchase, as we would need at least 3 of these. The MCU also needed to have Wi-Fi and Bluetooth capabilities, the ability to use UART and I2C, an analog digital converter, and other specifications we go more in depth in our paper. As you can see here, the ESP32 was one that fits our needs the best, as it has all the requirements we needed with all the added benefits of having a dev board for the specific MCU to do tests on. This also was a very suitable MCU for us, as many of us already had ESP32 dev boards with us to do testing on, which reduced the overall cost of this project.
For our project, selecting the right single-board computer was essential to ensuring smooth real-time processing while keeping cost and power consumption manageable. We compared 5 different options: NVIDIA Jetson Nano, Google Coral Dev Board, Odroid, Upboard, and the Raspberry Pi. Our evaluation focused on key specifications such as CPU, GPU, RAM, storage, and built-in connectivity like Wi-Fi and Bluetooth. We needed a board that could efficiently handle our machine learning model for skin tone detection while maintaining low power consumption. The CPU and RAM had to support real-time processing without excessive lag, and dedicated GPU was a plus for image processing tasks. In addition to performance, we considered hardware integration. Built-in Wi-Fi and Bluetooth would streamline communication between the system components without requiring extra peripherals. Storage flexibility was also important for hosting datasets and model files, as those can get really large. Lastly, affordability and developer support played a major role in our decision. A strong software ecosystem with active community resources was key for troubleshooting and long-term viability. After looking at all of these factors, we found that Raspberry Pi was the best choice for our project. When selecting a machine learning framework for this project, our primary focus was on efficiency, compatibility, and real-time performance. Since the Raspberry Pi is a resource-constrained device, we needed a framework that is lightweight and optimized for image processing without requiring a dedicated GPU. This led us to compare OpenCV, TensorFlow, and PyTorch, evaluating their suitability based on factors like cross-platform compatibility, pre-built image processing tools, and overall system performance. A key requirement for our system was built-in support for face detection and skin tone analysis. TensorFlow and PyTorch are widely used for deep learning applications but are computationally intensive and often require hardware accelerators like GPUs to run efficiently. While TensorFlow Lite offers optimizations for embedded devices, it still introduces additional processing overhead. PyTorch, on the other hand, is primarily designed for research and experimentation, making it less ideal for our real-time applications on the Raspberry Pi. Ultimately, OpenCV emerges as the best choice due to its optimized computer vision algorithms and built-in face detection capabilities. It allows us to process images with minimum latency, enabling the system to dynamically adjust lighting based on detected skin tones. Additionally, OpenCV's strong community support and extensive documentation make development and troubleshooting more efficient. This framework provides the right balance of speed, accuracy, and resource efficiency for our project's needs.
When building an imaging system, the sensor selection is the first step, since this is what determines many of the important parameters. However, my optical components hinge upon being compatible with our hardware and corresponding software capabilities. Because our team decided to use a Raspberry Pi for the ICU, I could only choose a sensor that was suited for the Pi. Therefore, we looked at Pi cameras. Now, part of the reason we chose this model was because of its sensor selection. So for the scope of our project, I went with a high-quality camera, since the sensor size allowed for versatility in field of view and focal length. Many others came with lenses already built in, which would interfere with the lens design. Now, with the lens design, we are creating a telephoto objective that combines a large positive and negative lens. The positive lens is there to collect as much light as possible into the system, while the negative lens will magnify our image so that we capture our subject's face and neck clearly. Since CHROMA focuses on color, I need to ensure that the chromatic aberrations were reduced while also remaining in budget. There are a few ways to do this, namely an achromatic, apochromatic, and super achromatic system. An achromatic system corrects 2 wavelengths, while apochromatic corrects 3, and super achromatic 4. The cost goes up significantly as more wavelengths are corrected. So we went with an achromatic system, and while only 2 wavelengths are corrected, red and blue, this suits our needs since these are the wavelengths we will be focusing on.
In selecting our LED technology, we looked at the wide variety of LEDs available across the market, including single color, bicolor, meaning 2 different shades of white, RGB, red, green, blue, assignable RGB and RGB integrated circuit, RGB white and then warm white, and then finally RGB CCT, standing for correlated color temperature. All of these have their own pros and cons, but ultimately we ended up deciding on the RGB CCT, as those have the trifecta of what we need, meaning they are tunable in color, they are tunable in their white color temperature, and they output a broad white spectrum, which is absolutely necessary to ensure accurate photography. Upon selecting CCT as our method of controlling the color temperature, we were able to move on to selection of the LED hardware. In our selection, we looked at 3 different companies: Superbright, Superlighting, and Waveform. While all of them had a fairly similar color temperature range and the beam angle was similar, we started to see a standout difference with Waveform in the quality of their color rendering index. This is also reflected in the cost, but in order to ensure that we are accurately photographing our subjects, we believe it is necessary to have these high quality parts to ensure accurate lighting. This table gives our engineering specifications. with the key specs in green. Our full system will have a response time of 20 seconds or less. The image capture unit will have field of view of 30 to 35 degrees to create the portrait-style image at a working distance of 6 feet. The LED panels will have a maximum power consumption of 48 watts and the ICU a max of 10 watts. The LED panel will emit a color temperature range from a very warm 2700 Kelvin to a cool daylight of 6500 Kelvin, and the image processing will take 3 seconds or less. This table gives our engineering requirements. Our key requirements include the accuracy of skin tone ID under both neutral 5500 Kelvin light as well as the test lights at a rate of 80% or greater and 70% or greater respectively. Our other main requirement is the frequency in which our system works 100% accurately in adjusting the in-image appearance of that person's skin tone. Other requirements include the accuracy of grouping for the LED presets, as well as the color rendering index, or the CRI, of the LED panel being an 85 or higher.
In this hardware diagram, it shows how the system will operate, and to the right-hand side are all our legends signifying who is working on which subsystem and what each of the arrows mean. As seen here, the information needed is taken by seeing the subject with the use of our image capturing unit, labeled here as the ICU, and relaying that information to the light adjusting PCBs that I will talk about later. This PCB will then help control the fill light boxes that will be made to then shine the correct brightness, temperature, and color of the light onto the subject.
This diagram outlines a software workflow for dynamically adjusting lighting in real time. The process starts with motion detection on the ICU. If no movement is detected, the system remains idle. Once movement is detected, it verifies whether the subject is human before proceeding to the skin tone analysis. Based on the identified skin tone, an optimal lighting setting is computed and transmitted using a lightweight messaging protocol to the ESP32 microcontrollers, which control the lightbox LED panels. This ensures efficient, low-latency communication, allowing lighting to adjust dynamically for proper illumination and enhance image capture quality. Training a machine learning model involves leveraging OpenCV to detect facial regions and classify skin complexions based on Google's Monk skin tone scale. Instead of collecting and labeling thousands of images ourselves, we're able to use Google's Monk skin tone examples dataset, which provides a diverse and well-labeled skin tone samples. This saves us significant time and effort in training, allowing us to focus on fine-tuning the model for real-time performance. By using supervised learning, the model learns to classify different skin tones accurately and adjust lighting conditions accordingly. Since the model is deployed on a Raspberry Pi, it must be optimized for efficiency to ensure low latency interference, making real-time skin tone-based lighting adjustments possible. This demo showcases our machine learning model in action, running on the Raspberry Pi to detect and classify skin tones using Google Monk skin tone scale. As seen in the image, the system successfully identified multiple subjects, placing bounding boxes around our faces and assigning them to the closest matching skin tone label. In this case, my face is classified as Monk 3, while my mom's face is labeled as Monk 4. It is worth noting that lighting conditions influence classification, which is why my face appears slightly lighter due to the better illumination. The model uses OpenCV to extract my facial features and map them to Google's MSTE dataset, ensuring consistency in skin tone classification. This capability is crucial for enabling dynamic lighting adjustment, as the system can now recognize different skin tones and apply personalized lighting recommendations in real time.
This is the schematic for our PCB design that will go into our lighting panel and control the high CRI RGB CCT LEDs. There is a regulator on the board that steps down the voltage from 12 volts to 3.3 volts to power the ESP32. Not shown on the schematic is another regulator that will be used to help convert the incoming voltage of 24 volts from the power supply down to 12 volts for the PCB. The power supply is 24 volts, as that is what the LEDs require to be run. The major components here are the transistors, which help with the high CRI or color rendering index to channel the light to each LED. Adapted from the schematic, shown here on the top left is the drawing of the PCB made using KiCad. We optimized the layout of all the components on the PCB to minimize space utilization while ensuring adequate spacing, accommodating trace routing. Through holes were added onto the PCB to allow us to use wires and couplers in our system, which provides us with the added benefit of keeping the board modular for maintenance and ease of use when needing to switch components or program our ESP32 microcontroller. On the bottom left is the 3D mock-up of how the PCB will look. The PCB as of right now is currently a manufacturing process made by JLC PCB. This company was chosen to manufacture our PCBs for their high quality and quick turnaround times. JLC PCB offers to install parts onto the PCB at an added cost, but to keep our expenses low, we opted to order all the components separately and solder them to the PCB by hand. The next step after receiving the PCB is to test all the connections and make sure that everything that has been designed on the PCB functions as intended.
To achieve our goals and create an imaging system with a horizontal field of view of around 30 to 35 degrees and with an effective focal length of 11 millimeters and the subject about 6 feet away from the system, the following lenses were chosen: a 3-inch plano-convex lens for collimating, a 2-inch plano-concave lens for magnification, and a 1-inch cemented achromatic doublet. This system is essentially emulating a 50 to 85 millimeter telephoto lens for cheaper while maintaining good quality images. These lenses are commonly used in portrait photography, which is our primary focus in this project. The lenses scale down in size to ensure that the image is not cut off, but instead will be overfilled. As shown in the diagram, the 2-inch lens only partially collects the rays from the first lens, but if they were to be the same size, the resulting image would show the outline of the first lens instead of solely focusing on the subject like we need it to.
The LED panel itself will be 9 by 9 inches and contain 96 chip-on-board LEDs. The sides will each have front reflectors to help minimize light leakage out of the sides, ensuring all of the light gets reflected into the diffusion panel and ultimately out towards the subject. For the physical LED panel, we have not yet built a full prototype. However, we have been able to do some calculated performance evaluations. When compared to our specifications, our calculations far outstrip our requirements. Our lumen output is over than doubled, especially if we are lighting both, if not all, of the lights at once. Our current draw stays under our maximum of 2 amps. Our total power draw is calculated at 46 watts. Our color temperature range is wider than our specification. Our color rendering index is significantly greater than our initial specifications, and the specialty color rendering index of R9, which is important for accurately reflecting off of the color of human blood, is a very successful 90 or 80, depending on if we're using a warm or a cool white.
During initial testing, we were able to utilize some lower CRI LED strips made by Govee attached to an ESP32 dev board. We also have 2 power sources for this test, one for the ESP32 dev board and one for the LEDs. The ESP32 was loaded with the software we will be using for this project called WLED and is specially designed for projects involving ESP32 MCUs and LED strips. In this clip, it shows the ESP32 is being able to talk to the computer wirelessly via Wi-Fi to control the colors on the LEDs.
Here we have our budget outlined with the main components for CHROMA to be functional. These prices do not include shipping or other additional costs as of now, which is why our team has a maximum budget we aim to be under after testing and housing are complete. This allows us some cushion for any issues or unforeseen costs we may encounter before the project is fully realized. The work distribution for this project is separated into primary and secondary roles. As you can see, each person's primary role corresponds to their academic focus. Mads oversees the panels themselves, their construction, configuration, and the lighting control algorithms, which are based on skin tone. Juan programs the software on the Raspberry Pi and the MCUs, which include the image processing, machine learning model, and communication between the ICU and the panels. I am creating the optical system which will feed the input to the Raspberry Pi, as well as the housing for the entire ICU. Nicole is responsible for the electrical components, primarily PCB development, wiring, and soldering. The secondary roles, highlighted with orange bullet points, are a method to keep everyone on track. Some are outside the scope of the individual's knowledge, but we are aiming to understand all roles in this project, even if it is only at a simpler level. To date, we have almost all of our vital materials, with the exception of our PCBs as previously mentioned. We have completed preliminary testing of our materials individually, and the finalized designs for the entire system are almost complete. Our milestones on this timeline are color coordinated to indicate the responsibility, consistent with the work distribution. We hope that by the first week after the critical design review, the PCB and imaging system will be finished and completely tested. The following week will be dedicated to the software for the skin tone analysis, as well as the mapping table and corresponding lighting algorithms. Finally, the housing will be the last part before the midterm review so that our group can work towards a finalized product. Our goal is to have a full system respond in real time before the midterm review, which is about a month before the final demonstration. If that goal is not achievable, that time is allotted to any further testing that will be necessary and fine-tuning of the project so that our system works efficiently within the parameters set forward. The CHROMA team thanks you for your time and consideration, and we hope that you enjoyed our presentation.